Jack Conrad, using transformers to improve answer retrieval for legal questions. Okay, so consider that you're working at a legal tech startup company named Litimate, a friend for legal research, which is a fictional company. You want to create a question answering system because you've been receiving complaints from your users that search doesn't satisfy their natural language queries. Well, you have access to a large legal database and you have user query logs. In addition to all that, you have a team of subject matter experts. Is that going to be enough? We'll see. So some of the strategies you could use for question answering is answer snippet identification. This is similar to the squad problem. And the pro is that you're able to produce concise answers from any length documents. But the cons are that legal documents are often really long. Inference over long passages can be really slow, or they might not fit into your transformer window. And then in addition to saying whether or not the passage is a sufficient answer, you need to identify the boundaries of the snippet. So another strategy that can be employed is answer generation. The nice thing about generation is you're able to produce unique answers to any kind of question, but the answers often look really nice to the untrained eye. However, it's really difficult to control the generated text, and the answers are not legally sound, which is not, ideal for the legal company. And the structure of legal text is not trivial, and there's potential for harmful bias. The final task you could do would be question answer classification. Some of the pros is that passage classification is a lot easier to implement than snippet identification or generation. The answers are legally sound because you have subject matter experts curating the data. And there are a larger variety of model architectures that you can use for the task. Some of the cons, though, are that you need to have some extensive pre-processing and cleaning in order to have a robust system. And then content might not exist for a particular query that your user is asking. So we'll take on the question answer classification strategy. So some of the ways we can do this, one, we could use classical machine learning, where we use like a bag of words approach, or we could use embedded features like your glove embeddings. Classical machine learning models are usually faster and smaller than transformers, which makes them easier for a production system. However, because of their small size, they're less capable of interpreting legal concepts. Pre-trained transformers, however, are able to utilize the power of transfer learning to learn the English language or whatever language you're working in ahead of time. And then when you can do fine tuning on your specific legal data in order to gain more of a grasp on the legal concepts. Transformers, however, are usually larger models, which makes them better equipped to interpret legal language. However, because of that, they're slower and they're more prone to overfitting. So let's talk about how we would build this pipeline. So the plan of attack first, we need to talk about how we would pre-process and clean the content, how we would actually do the fine-tuning of a pre-trained transformer, how we can use a lexical semantic overlap mechanism to have a more fine pool of candidates, and then performing the actual inferencing on the retrieved candidates. So content handling, oftentimes legal content has this hierarchical structure where you have a document, and then within each document, you have several sections, and within each section, you have several headings, and then finally within each heading, you have several paragraphs. So it's a lot easier to take on individual paragraphs than taking on the entire document. And so also legal text can be noisy and contain superfluous information for a transformer model. So as a result of that, you can use some techniques like regular expressions, rule-based filtering, et cetera, in order to have something that's easier for a transformer model to understand. So if you look at the example to the right, this is just a toy example I made up. Sentences that contain 4 more information, ... usually are not content bearing for a transformer. If there's a sentence that doesn't actually contain English words or parentheses, we want to get rid of that for feeding it to the model. However, it's important that the answer presented to the user is up above, because a lawyer, a legal professional, is interested in the citations and the additional information. So doing this iterative model training cycle, we have our user log of queries, and we can take our initial classifier and run some predictions. And so with these predictions, we have some candidates, some QA pairs, and we can use our subject matter experts to assign grades to those. And once we have those graded QA pairs, we can train our model, our transformer. As you can see, our transformer here is working real hard. And we iteratively repeat this process until we have a model that we are satisfied with.
5 more minutes, Andrew.
So now the application pipeline. So what that would look like is it ingests user queries. And oftentimes you have a lot of content. So instead of using a single machine, it's advantageous to use a cluster of machines. And because inferencing over passages can take a while with a transformer model, we don't want to run inference over all of the passages in our content. So we have to use a lexical semantic overlap technique to reduce the size to something smaller, something more relevant. And we take the top end. And n can be 100, 1,000, 10, 50. It's up to the designer of the system. And then once we have that, we can pass those to the transformer model and then give the top answers to the user. Okay, so now I'm going to talk about an illustrative question answering experiment. This experiment is not indicative of what an application pipeline would look like, but more so is to demonstrate the power classifier over traditional systems. So the data that we used was the privacy QA data, which is an open source data collection concerned with digital privacy. You can see the data set specifics here. The data is often really challenging. The user queries are often not very idiomatic, can sometimes contain misspellings. The answers often are run-on sentences, contain links, things like that that can be distracting to a model. The green answer here is the positive labeled answer, and then the red example here is the negatively labeled example. And I chose those just to kind of illustrate how difficult it can be to do this classification experiment with this data set. So we're going to consider the setup where we have a baseline, which is a linear TF-IDF or linear SVM classifier with TF-IDF input features. We'll do 5-fold cross-validation and a randomized search to find the optimal hyperparameters. Once we have that done, we can take our transformer model, use that optimal fold that was found from the previous baseline, and then train on those QA pairs with their relevancy labels, and gradually unfreeze until the transformer is sufficiently trained. So now in the comments, you can feel free to place your wagers on who do you think will win this fight. All right, here are our results. As you can see, we have our 2 distributions below. The first distribution is the Roberta scores, so the type of transformer that was used for the experiment. As you can see, there's more blue-orange separation, which is what you want to see. And the black line is the optimal decision boundary over the test data. And then for the SVM, you can see the blue and the orange are closer together, which is not quite as ideal. We achieved a 31.6% improvement in the mean reciprocal rank, which is essentially a metric between 0 and 1, 1 being your answers are always at rank 1, and 0 meaning you never get your answer. So the baseline had an MRR of 0.1, which means on average, the correct answer was at the 10th rank. And we also had a 23.4% improvement in the F1 score, both of these results being statistically significant. So to conclude, question-answer pair classification is a viable way to answer user queries. Pre-trained transformers oftentimes can outperform traditional ML techniques, and we don't really need that much fine-tuning data, and it need not be excessively clean. And then finally, with the right ingredients in place, you can implement a transformer-based QA system to satisfy your user's natural language queries instead of relying on some sort of lexical matching in search. Thank you for your time, and I'm happy to answer any questions now.
Thank you very much, Andrew. So we have some questions for you. Is there any special reason why you used a data set consisting of privacy policy questions during the experiment?
That's an excellent question. The reason for it is we wanted to choose a data set that was open, a publicly open domain, or not domain, available to anyone. so that one could reproduce the results. We didn't want to use any kind of internal data or things that we weren't able to show. And the privacy QA data, though it's not specifically just like general legal, it's close enough to the legal domain such that it can be illustrative of the types of problems you would see in that type of system, if that makes sense.
Okay. And what measures did you take to avoid bias in the selected data set that incorporate specialist answers?
To avoid bias, well, so the data was curated by a different organization. So we didn't actually have, take any specific care in bias. However, there was a little training, testing, contamination in the queries. So we did have to remove some of the queries from the test set and put them on the train set in order to have independent queries between those two sets.